You are the host, and I will share the YouTube link.
Awesome.
In social media.
So thank you.
Best luck.
Thanks a lot. Yeah, I can see that I am. Gotcha. Okay. All right. So I can start this. And I can start sharing my screen. Where's this one? Okay. Can you guys see it?
Yep.
Yes.
Awesome. I'm going to mute myself and I'll come back around 11. Okay, everyone, it's 11 o'clock. We're going to give another 2 to 3 minutes for people to join in, and we are going to start roughly 11:03 with our content. Thank you. All right, everyone. I believe this is the time we should get started. So welcome everyone to the GPU Accelerated Data Science. This is our webinar on GPU data science. In this particular installment, we're going to be talking about the accelerated data frames, QDF, from Rapids, as seen from the perspective of pandas users. Very quick agenda for today. I'm going to give you a very quick rundown of what Blazing SQL is. We are going to be using app.blazingsql.com today. So just an earlier of introduction of that, and also a very quick introduction to Rapids. And then I'm going to hand it over to Justin Brandenburg from NVIDIA to give us a hands-on part on introduction to QDF from a pandas user's perspective. We're going to have some Q&A time at the very end of this session. So let's start with Blazing SQL. Blazing SQL is a GPU accelerated SQL engine for the Rapids ecosystem. What do? We allow you to run SQL queries on QDF data frames, or as in this particular example, files. In this particular example, this is CSV, but it can be Parquet, it can be ORC, or any other format that is supported by Rapids ecosystem. In this particular case, we read a CSV file, create a table on top of that directly from a QDF data frame, and then we can run very quickly a SQL query on top of that to select how many records we have in that particular table. Blazing SQL fits nicely and complements the Rapids ecosystem. So Rapids is this whole end-to-end data science stack that runs on top of NVIDIA GPUs using CUDA underneath the hood with a very familiar Python interface. And what I mean by familiar is, as we're going to learn today, it's almost 99% equivalent of what you see and what you're familiar with using pandas. If you are familiar with scikit-learn, QML is going to be pretty much the same equivalent of what you see in scikit-learn, and so on and so forth. Blazing SQL adds another layer on top of that. So we complement the whole ecosystem, allowing you to run SQL queries against data frames, against distributed data frames with Dask, against distributed file systems, and so on and so forth. These file systems can be either local to your machine, to your cluster, or they can be located somewhere in the cloud. In this particular case today, we are going to be using S3 from AWS. And then if anything doesn't fit natively on a single GPU, in case of Rapids or Blazing SQL, we have the ability to scale it out to hundreds of machines using Dask. So these machines can be either with a single GPU, multiple machines, or Dask also supports building clusters where each machine has multiple GPUs built in. So if you are using the latest and the greatest DGX2 from NVIDIA with 8 A100s or V100s in it, you can definitely run Rapids and Blazing SQL on top of that. Very quickly, this is effectively the stack that we use. At the very bottom, we have CUDA and CUDA libraries. We also, on top of that, we built the storage plugin, so it allows you to read data from either local machine or a cloud repository. And we have a bunch of QDF C++. Blazing SQL builds on top of that. We use Apache Calcite to parse the SQL queries and create this relational algebra. And then RAL, the relational algebra engine, takes that and runs, effectively executes the kernels that trickle down from the Python through Cython to run the QDF kernels. On the left-hand side, you see Dask. We use Dask for communication. Right now, TCP is by default. And we are in very advanced works to implement UCX that will enable to use constructs like InfiniBand to communicate between clusters, further taking the speed one notch further. In terms of how we fit into the whole Rapids ecosystem, as I mentioned before, Rapids ecosystem is this end-to-end data science stack. So it deals with data preparation. And in this particular case, if you use Rapids on its own, it's cuDF's job. Then cuDF, once you've done the ETL part, you can hand it over to model training, and you have ability to use QML, QGraph, and whatnot. You can easily move the data to use deep learning frameworks like PyTorch, Chainer, MXNet, and whatnot. And also the visualization part, you can utilize GPUs and utilize underlying cuDF to visualize your data using cross-filter or data shaders. Blazing SQL fits at the very beginning, so it's kind of equivalent and substitute of cuDF. Some things are better and easier to be done in cuDF using pandas API. Some things are easier to do using SQL. You have a choice of both. What enables that is the Apache arrows. So at the very bottom line, and the very bottom, we have this common memory representation of all the objects that we deal with. They can be moved between, GPU and host memory, and then they don't need to change. So we don't incur this constant copy and convert cost. That's what makes, on top of the usual speed you get from GPUs, that what makes the Rapids ecosystem so flexible and so easy to, and so fast. In terms of the normal data science flow, you have your data. So you have your data in CSV, Parquet, Org, Pandas, cuDF. It can be pretty much any format of these. If you want to use Blazing SQL, we import Blazing context and create a Blazing context object here. In this particular case, this is with default parameters, so you don't have to specify anything, but there's a host of parameters that you can customize the Blazing context. We register, in this particular case, in this particular example, we register an S3 bucket. The S3 bucket in this particular case, we call it bSQL. This is a public repository, public bucket that we have on S3 that you can read the data from. And then we create a table on top of that. In this particular case, it's the orders table that sits in this particular location on S3. And as soon as you hit Blazing bc.sql select star from orders, what Blazing context will do is just run that query, select all the records from the orders table that we've just created. It's as simple as that. I probably do not recommend doing that if your orders table has billions of rows, but you can add limit 10 and then retrieve only 10 records from that table. So that's the Blazing SQL. This is the ETL part of the data science journey. ETL, feature engineering, it's so easy doing Blazing with SQL and with cuDF. And then once you do this, we spend 70–80% of the time doing this type of work. You can hand it over to machine learning. It can be XGBoost, which is already GPU enabled. It can be QML that has a host of already built-in algorithm, machine learning algorithms that you can use to build machine learning, for regression or for classification, build classification or regression models. The options are limitless. Rapids ecosystem also supports graph analytics via QGraph. So if you need to do graph analysis, there's also tools to do that. So how do you get started with Blazing SQL and Rapids? The easiest way, and probably the most common way, is to use open source offering. So you can install Rapids and Blazing SQL via Anaconda, or you can download the Docker image and start running with Rapids, with containerized via Docker. The one thing that I should mention here is that you need a GPU, and not only a GPU, any GPU, but it needs to be an NVIDIA GPU that is of Pascal, coming from the Pascal family or above. So anything that is GTX 1080 Ti should work. Anything that's below, like 970 or anything like this, it doesn't. Rapids doesn't support that platform. So anything that is Pascal and above is good to go. Anything below is not necessary. Or, as we are going to use today, you can use Blazing Notebooks. Blazing Notebooks is a turnkey, no installation, no configuration necessary. You can just go to app.blazingSQL.com and start running your Rapids scripts and Rapids notebooks, developing with Rapids and Blazing SQL on that platform. We also support what we're going to use today is a shared offering. So the free offering, you getting T4, but it's shared across a couple of other people that are going to use that service. We also support and provide a private clusters where you can create clusters anywhere between 1 GPU to 64 GPUs at a time. All of these GPUs are T4s from AWS. And I believe Justin is going to show you that later today as well. Rapids on the cloud, this is pretty much the easiest way to get started with Rapids and Blazing SQL. Before we go further, we need to get ready. So I would ask anybody that follows to go to appblazingsql.com and open the new terminal window. So I'm going to do that right now. You need to log in with your Google account. I'm going to use mine. And as soon as this shows up, what we need to do is to remove the Blazing SQL Notebooks folder and clone this particular repository. So if you are joining us for the first time, all of the notebooks that we are going to use today, they should be there ready for you. If you are joining us for the second, or you've already joined us before for any of the webinars, we need to go through this process. This might take a little while because we are currently provisioning the service behind, but it shouldn't be too long. But ultimately, I'm going to go now to the GitHub repository, to BlazingDB. Welcome to Blazing SQL Notebooks. We're going to provide these links in the description on YouTube. And I'm going to paste that later on to the chat window. If you are joining us, we also streaming this particular webinars to our YouTube channel, so you can watch them later on demand. All of the notebooks that we use in the webinars is in the webinars folder over here. And today we're going to be working in the Rapids intro. So in particular, this is 02 Introduction to QDF for Pandas notebook. Now we can copy the link and let's see if we are here running. Not yet. Let's see if this is started. There you go. All right. So we're good to go. Right now, what we need to do, as you can see, I have webinars and I have Rapids intro, but I don't have the second webinar yet. So I'm going to open a new terminal and remove the Welcome to Blazing SQL Notebooks folder. That shouldn't take too long. And then git clone the repository that I just showed you. This way, we get the very clean, fresh start with all the notebooks that we need, and we can get started. So let me check if everything's over there. All right, webinars, Rapids intro, there you go. I have the 02. So for me, now would be a good time to introduce Justin. Justin joins us from NVIDIA, as I mentioned before. Justin is doing the developer relations for data science at NVIDIA. He has a wealth of experience with running distributed systems. And without further ado, Justin, I'm going to hand the reins to you and take it away.
Thanks, Tom. Just give me one moment while we transition. Go ahead and share my screen here. All right, I just need 1 second to be able to share my screen.
You should be able to do it right now.
Okay. Thank you, Tom.
Yeah, no worries.
So let me know if you guys can see this.
Yes, we can. At least I can. You might want to make the font a little bit larger, though.
All right. Hold on. Give me one moment.
Perfect.
Awesome.
Awesome.
Thanks, Tom. So as Tom said, my name is Justin Brandenburg. I'm on the developer relations team at NVIDIA for our data science ecosystem. And part of that ecosystem includes the Rapid suite of software libraries to do essentially the entire order of operations associated with kind of the data science workflow. This includes, data exploration, feature transformation, data preparation, model training and development, as well as model serving and model inference. But if you want to back up a second and you look back at where everybody kind of begins with kind of their data analytics, data science journey, it begins with first evaluating the data in a data frame format. And when I was starting with learning Python about 10 years ago, kind of my first entryway into understanding how the data object would be looking at, how I can manipulate it was within the pandas data frame format. And as we've gone along over the last couple of years, we started to see a lot of the utility that pandas offers in terms of how you approach problems, how you approach data, how you gain insight into that data. One of the things that NVIDIA saw was an opportunity to then enhance that experience, enhance that opportunity to innovate on your data, but now leverage the additional compute power associated with the GPU. Now, when you started your data science journey, maybe some of you thought that you would have to, graduate to, from pandas to PySpark or some other type of more complex system to be able to leverage larger data sets, more complex data sets, and more complex ETL workflows. What QDF and Rapids in general is trying to do is trying to make it so you don't have to learn a more complex syntax, a more complex programming paradigm. You can still use all the same familiar API components that you were using in Pandas, except now you can use them using QDF on top of a GPU. And that's what I want to show today. Is just kind of the slight variation from what you would be doing in Pandas and doing on a CPU on a Jupyter Notebook to what you could be running in a Jupyter Notebook on top of a GPU right here in the Blazing SQL platform, and still achieve the same types of results, but using the power associated with the GPU and the APIs that mirror everything that you would see in a Pandas API. So I'll just kind of walk through this. What I'm trying to do here is kind of walk you through all the steps associated with when you first get a data set. What are some of the first things you do to gain insight into it? You explore your data, you explore the size, how many columns, get a sense of the content associated with it, the types of data associated with it. So one of the first things we do, and most common data file formats that we work with, at least initially with the data set, is the CSV. So one of the things I want to do right now is to show you that if you're pulling in a CSV, you're going to be using essentially the same type of commands that you'd be using in Pandas. So if we import our Pandas library as PD, we can do the same thing with our QDF library as CD. And then you'll see here that if we're just pulling it in this case, from an S3 bucket location, we're just doing a PD read underscore CSV, same as what we're doing with a CD read underscore CSV. So all you're doing essentially is just changing the letters associated with the framework that's actually committing the function, but then you're getting your data in, and it's going to be the same format. It's going to be, excuse me, interpreted in the same way. And then now you can begin your standard steps of data exploration and familiarizing yourself with how you would analyze this data, but in a different type of hardware environment. So in this case, we want to just gather simple data statistics. What's the shape of our data, the number of dimensions, how many rows are there? In this case, there's 4,916 rows, and we have 28 columns. And what I'm doing here is I'm essentially showing you back to back the commands you would be giving if you're using pandas or using the QDF APIs. And as you can see, once you've loaded that data in and you've identified and given the name of your specific data frame, in this case, movies_PDF or movies_CDF, at that point, everything after it is essentially what you'd be doing in your standard pandas syntax. You know, seeing just what's your initial type of data looking like. In this case, you know, using the head function, just getting the first couple of rows, seeing the content of some of the columns and some of the rows of the data set you're working with. In this case, it's a fairly common data set. It's movies that contains, you know, the director, the first actor, the second actor, the third actor, the critic reviews, the box office gross, the number of Facebook likes, the number of actor one Facebook likes, things like this that you would most likely see associated with just kind of determining the overall popularity or success of a big blockbuster movie. One of the reasons I chose this data set specifically for this webinar is because this data set is made up of a variety of different types of data types. In this case, you have strings, you have floats, you have ints, you have discrete and continuous variables. And then associated with your strings, you have very distinct columns that would often need to be broken out into separate columns for a variety of other types of endeavors later on down the line when you're building models. So this data set offers us a really cool way to kind of compare and contrast the different commands you'd be using in the pandas API versus the QDF API. So as we're beginning to explore our data, you'll start to see, okay, well, I'm using my same normal Jupyter environment. I'm using the same types of commands I would be using in pandas, seeing kind of at least an initial subset or small sample size of what my data set looks like, you know, director name, number of critic reviews, so on and so forth. Let's get an idea of the actual data types associated with our data. So in this case, just leveraging the info function to get an idea of all the different columns associated with our data set. In this case, all the number of different types of columns, the data type associated with it, object, float 64, int, so on and so forth, all the way down from the color of the movie, all the way down to the aspect ratio and IMDb score. Do we have to do anything different with the QDF? Absolutely not. You're still leveraging kind of the same functional command that you'd be using, except you're running on a GPU. So you can literally translate your code, and all you'd be doing is essentially calling the first initial data frame initialization, and then applying all the same similar types of API functions that you're using before, but now you're doing it on top of a QDF instead of a pandas data frame. So you can see we're still leveraging all the different the same types of functions that we did before, but now we're doing it on the GPU. Let's get an idea of the columns. Same thing. You know, the creators of QDF saw the popularity of pandas. They saw that users were, you know, not inclined to necessarily migrate right away to just adjusting all their code base and all their methods and approaches to how they evaluate data to something like a PySpark or some other type of tool for data exploration. Users have consistent habits associated with how they approach their data, and what QDF does is leverages those existing habits by converting them into just a QDF API, which mirrors essentially the pandas API. So now that we have kind of an initial idea of what we're working with associated with our data, what about if we want to just go ahead and, you know, take subsets of this, you know, start kind of subsetting it, selecting different filtered components based on, you know, a data type, whether it's a number, whether it's an object, something like that. So how would we go ahead and specify this in a pandas versus a QDF? Essentially exactly the same. You're still going to be selecting data types, and you're just going to be including numbers, and you'll just take a subset, especially if you just want to see what you're working with. So we're just going to looking at the different columns that are numerical or continuous. Same thing for QDF. Same syntax, same command. We're just literally applying it to a QDF data frame instead of a pandas. How about if we want to do it for just specific floats, not necessarily ints or just overall number of types of columns? Here we can go again, just applying it and specifying it specifically within our API using the same function, selected D types, and then taking a subset just to evaluate our results to make sure that they match, to make sure that we're getting consistent results across both frameworks. So in this case, our movies PDF is returning the same thing that our movie CDF does when we both specify the selected, just select the columns that are float data types. Let's move on to discrete values. So in this case, discrete values, anything like an object. So in this case, the actor's name, the director's name, the name of the movie. What are the types of columns associated with this? The type of genre, so on and so forth. In this case, we're just doing the same thing, except now we're just selecting object instead of numeric number or float. So you'll see, we have Pirates of the Caribbean. My son loves this movie. It's a great movie. I've seen it a lot over the last year, but now we can start to see all the associated components, or how this essentially movie was evaluated from a data perspective. Who is the actor number one? Johnny Damon. Actor number two, Orlando Bloom. What are the type of genres that it fit in? Well, it fit across multiple genres: action, adventure, fantasy. What was the specific actor 3 name? Was there any type of correlations associated with the type of actors versus the type of genre? These are all the types of things that we can start to consider as we start to familiarize ourselves with the content of our data. And as you can see, as we did before, the selected data types, we're just doing the same thing that we did in our pandas API, except we're applying it now on our QDF. And the results are the same, and we still have the same capability to now approach this data set using the Rapids suite of libraries, just as we'd be doing if we were working on a CPU on our local machine, or using something like pandas and scikit-learn. So we can start to develop our intentions associated with how we're going to approach this data. What are some of the things we're going to need to do? What type of transformations are we going to do? Are we going to have to, do some one-hot encoding? Are we going to have to, split up a couple columns to give them their own distinct columns, specifically genres, for example? So now we can start to come up with an idea of some of the types of data wrangling methods that we're going to have to apply on this data set as we continue to work through it to get it in a proper format to begin additional analysis. So let's start performing, some initial data analysis and just get some standard summary statistics, which you would essentially apply for all types of data sets. What are some of the basic types of things when we would first walk into a data set? We'd first want to know, specifically associated with the continuous variables, is what are some of the outliers? What are the means? What are the max? What is the standard deviation? To try to come up with an approach of, okay, are we going to have to handle these types of outlier random rows, or is everything somewhat self-contained within specific standard deviations of a normal mean? These are all the types of things that you want to kind of consider when you start to develop, or how you're going to prepare your data. The great thing is that if you've done this before in pandas, you can do it now in QDF in Rapids. We're literally using the same describe method, excuse me, after we've only selected the columns that we want to apply the describe method to, in this case, the numerical columns, the continuous columns, so on and so forth. So now we're actually going to be able to compare and contrast exactly the same columns, exactly the same summary statistics associated with these two data frames, and we're going to receive the exact same feedback because literally we're just telling it to do the same thing, but now we just want to see it on a different data frame object. Let's look at it associated from all discrete values, in this case from some of the categorical variables. So if we look just from an object type, what are some of the different counts associated with directors' names? So how many unique directors do we have in this data set? 4,814. What's the top one that we would normally see associated with a specific frequency? Well, in this case, Steven Spielberg. Actor 2 name, Morgan Freeman. What's the number one genre just individually by itself? In this case, drama. But it's not. But that's interesting to note, because when we saw there were other genres that were kind of concatenated together. So in this case, are those unique, or have they already been spaced out? So now we're starting to see, okay, there's some interesting things associated with our data. Oh, excuse me, funky internet connection here. And then here's something I like to do just to get a better idea and get a better look at how my data is fitting, especially if we have a large number of columns. And this can be done in pandas too, but I just wanted to show you this is something that I normally do when I'm kind of evaluating my data, is just do specifically with a transpose, is to just get an idea, a better view, especially if I have a large number of columns. And like I said, you can do this in pandas as well, but I just wanted to highlight that you can do it in a CUDA data frame. Sorry, let me check this.
Justin, I think your server just shut itself down. Yeah, it's stopping right now. So you have to wait before you can restart it.
Yes, you're right. Thanks, Tom.
Yeah, no
so
worries.
yeah. So just a quick aside, guys. So I spun up a cluster, but I had to auto terminate or auto suspend to shut down after 15 minutes if I don't go ahead and execute any queries in this notebook, which is great to have in case you accidentally leave your GPU on and you want to manage your costs. So in this case, if I accidentally had to walk away or something like that, and the GPU or the cluster associated with it isn't going to execute a query, it knows to shut down because it's saying it's not being used anymore. So this is a way to manage your costs and make sure your utilization is more efficient. So that's great. Thank you very much, Blazing SQL, because I don't want to use all my credits. So let's look at this a little bit in greater detail. So again, if we wanted to look at covariance associated between two continuous variables, I apologize again, guys, it's going to take a moment. Or if we wanted to look at correlation between two continuous variables. So say we had an initial idea associated with what's going on specifically with some of our data sets. If we just wanted to kind of make an initial assumption on, okay, there's probably a high correlation between a couple of actors, or whether a movie gets a specific number of Facebook likes and is highly correlated with the actors in it. Not necessarily the first actor, the second actor, the third actor, or second actor, excuse me, but it could be the third actor. What are the correlation things there? Well, it's probably close to say that if they're labeled the third actor, then the number of Facebook likes isn't probably highly correlated with that particular actor. As you can see here, it's 0.27 for both our pandas data frame as well as our CUDA data frame. But what I'd like to show here is that you're still leveraging the same syntactical components that you would be seeing within the QDF suite of functions that you would also be doing in the pandas API. In this case, specifying my data frame, specifying my column, specifying the function, in this case, the covariance function, and then specifying the additional column within my data frame that I would like to apply it on. As well as here, same thing with the correlation. So as often when we start to do some additional types of analysis, we want to infer maybe some additional grouping. So especially if you have a series of discrete variables and you want to be able to calculate frequencies, you want to be able to calculate totals, you want to be able to calculate number of specific objects associated with some discrete variable, you want to be able to use kind of the group by function with it, which is a fairly standard function within pandas and utilized in a series of ways. In this case, I'm kind of comparing, in this case, our actor number one name, our actor number two name, and often when you see two successful actors and that they have one successful movie, there's a higher likelihood, at least in my opinion, that there'll be another one. And so what is the overall gross between these things? Specifically, if we combine them, and then we sum across the gross number of dollars associated with it. So as you see, I'll specify my two inputs or three input columns that I'm selecting, that I'm then going to apply my group by on. So the first two, and then apply the sum on, in this case, gross. And then if we compare this to our QDF command down here, you'll see it's exactly the same. Everything from selecting the columns to the specific group by function to the subselect of which the group by will be applied on, and then the actual summation of the numeric value, in this case, the gross movie dollar amount. So now we've done some initial data exploration, some data analysis to familiarize ourselves with the contents of our data, especially very important, especially if you're not necessarily familiar with the data sets that you're getting, if they're coming from a third-party provider, or this is your first time and you're just trying to evaluate to gain some insight. one of the things that you'll often do before you can actually start modeling on this data is some standard data preparation. Often data transformations, splitting columns, one-hot encoding, so on and so forth. And so one of the additional kind of feature associated with this particular data set is the genre column. And as we pointed out before, the genre column is made up of a series of combinations of ensemble genres. So in most cases, it could be, I'm gonna go ahead and restart my cluster, guys, so that'll stop happening for us. Apologize again for that. So what you're seeing here is that we have, in most cases, a combination of different genres that are smashed together. So what we're saying here is that, for one record, the genre is action/adventure/fantasy/sci-fi. Another one is action/adventure/fantasy. So in some cases, a movie could be just a single genre, or it could be 4 genres, or it could space across 1, 2, 3, 4, 5, 6, 7 genres. So how do we kind of break these things out? So then now we can start to see, if there is a specific primary genre that this is hitting, and then there's complementary genres that could possibly hit that, then they would also hit those specific demographic groups. How do we kind of break this out to then start developing some models on that? Well, in this case, if we wanted to do that in pandas, we would just essentially here take the subset command, where we're actually taking the movie's PDF, the genres column. We're going to do the string split on the pipe here. We're going to expand true to give, then instead of just splitting it and then essentially giving each individual genre its own token within a list, it's going to now break it out into its own column. And then we're going to add a prefix to then say, now this new column that are created will then be genre_0 or genre_1 or genre_2. And when my server gets up and running again, then let me go ahead and rerun this for you guys. Let's go ahead real quick. Go ahead and run all cells. Let's go ahead and load in the data for the first time, because now the cluster is starting cold. So now it's going to have to pull all this up again. What I'm doing here is, because now that we've gone ahead and used the splitting the genre column using pandas, what I want to show is one of the slight distinctions, or maybe slight differentiations that you would get between using pandas for your column separation than you would be using QDF. And so, as Tom mentioned in our initial discussion when we were first going through the introduction for the webinar, that the QDF API mirrors almost all of the pandas API, but there are a few exceptions. And one of those exceptions in this case is just the add prefix component, which doesn't necessarily add much, but it does mean that when you do split a column, then when you're essentially creating these new columns, they're just assigned an initial value and not necessarily a column name that you can use to discern and then use later on to manipulate or apply to a specific vector. Let's go ahead and check up here. And I think I need to reload. Restart the kernel.
I think you might need to refresh the whole page.
I think you're right. Thank you, Tom.
Yep, no worries.
Give this one moment.
And if not, you might want to go back to the app and then just do, it might have assigned a different IP. Yeah.
Yep, you're right.
Now we should be good to go.
All right, thanks, Tom. Let's go ahead and rerun this real quick. Load all the data in. take just a moment here. All right. So what I'm doing here, and I just want to add this in here. Is that you'll see within the associated prefix is that now, once we've expanded the original genres columns, now it's action has its own column, adventure has its own column, and then also the column names are genre 0, genre 1, genre 2, so on and so forth. Now, one of the distinctions is that we won't necessarily be able to do that with our QDF. And as like I mentioned before, when we say the QDF API mirrors almost the entire pandas API, this is one of the few that isn't necessarily been developed yet, but we're working on getting it there. But a quick move around will be that we'll notice that, hey, we need 8 new columns that will be needed to add it to our data frame. So if we go ahead and look at them, and now that we've expanded using essentially the same command that you see here, where we selected the genre, we did a string split on the pipe, and then we expanded it to true, but we don't have the ability to add a prefix to then generate a new column name. So now they've just been assigned specific integer column names that if I did want to go ahead and rename, I'd go ahead and just grab the ones that are the genre fields. In this case, 0, 1, 2, 3, 4, 5, 6, 7. I'd apply and get them the new names. So in this case, genre 0, create a new list, and then I'd create a dictionary where I'd zip it up. So I'd take my initial list of the initial column names with my new list of column names, and I go ahead and QDF does have a rename function where you can pass it a column equals a dictionary that you've now specified of the original column names, in this case, 0, 1, 2, 3, 4, 5, 6, 7, and the new column names where we're going to specify genre 1, genre 2, genre 3. And now that we've applied that, you'll see that our output now mirrors exactly what we got from our pandas transformation. So it is one just initial type of differentiation, but with the overall goal that you can just do just a few additional lines of code, you can meet your output and get the exact type of results that you're looking for that meet exactly the type of expectations that were set forth if you're using the pandas API. So now that if we look at our data a little bit closely, we've created a series of new columns, and they're all discrete value columns. So what we want to do is perform some one-hot encoding if we wanted to then start doing some advanced machine learning analysis on top of this data. So if I wanted to select a specific column, in this case, I'll select genre 0 to then perform one-hot encoding on, and I'll go ahead and concatenate that one-hot encoded column and then apply it back to then, so it's combined with my initial column, data frame. I'll be able to essentially perform that and get the results using the specific pandas API. So in this case, I have my genre 0 column, but when the genre was game show, history, horror, music, so on, musical, and mystery, so on and so forth. But now I have a series of dummy variable columns that now I can be able to pass into my machine learning model, depending on the type of model I choose. The great thing is that QDF also has the exact same functionality, and I'll let you apply it and on top of your data to give you the exact same type of analysis, except you no longer even have to essentially use the concatenate because it just assumes that you want to include it into your initial data frame. So I'll go ahead and use the same get dummies that you would use in pandas. The specific data frame, in this case, genre CDF, specify the column that we're applying the dummy columns on, the genre _0, and then what the new column's name will be. So this is a slight distinction from what we saw before, where we were doing an add prefix. Now, because we're doing one-hot encoding, the columns will actually now have this prefix already attached, as you'll see here. So that's the end of this particular notebook, but what I've tried to convey in this session is to just how you would approach at least your initial data exploration needs if you're using the pandas API, And then what would it take to transition that into a QDF? Honestly, the learning curve is flat. It's just a process of specifying the package that you want, understanding that you're running on a GPU, and then going ahead and importing those packages. And then the only variability associated with it is specific to just how you import your actual initial data frame, or how you initialize your initial data frame, excuse me, and whether it's a pandas data frame or a QDF data frame. And then you can then start to transition and apply the same logic you'd be using in pandas, but just on a QDF. And I just want to do a time check. Tom, are we okay for time?
I think we still have like 5 minutes, so you can still do the Dask intro.
Awesome. So in some cases, you know, when you've been working with pandas, in some cases you do reach a limit of how much data you can actually perform your analysis on. Specifically just on like a local MacBook or just your local machine that would essentially run out of resources depending on how big your CSV or other type of file that you were importing into a data frame eventually got. And in some cases that would be when you would then necessitate to move into kind of a distributed parallel computing environment using something like PySpark, you know, initialize a PySpark data frame, and then perform a series of transformations to be able to analyze your data, and not necessarily using the same types of transformations that you'd be using in pandas. One of the things that QDF has been able to do is then now combine its effectiveness associated with this API with Dask, which is a distributed compute framework, which essentially takes your QDF data frame, and you can both also, Dask can also take your pandas data frame as well as your QDF data frame and distribute it out across a series of servers. So in this case, if I go ahead and specify, okay, I want to use pandas, but I also want to have a Dask data frame, I can go ahead and read my data frame in as a pandas data frame, and then literally convert it from a pandas data frame into a Dask data frame. And now if I have a series of servers or CPUs that I can distribute this data frame on, I can go ahead now and apply it across the number of available servers. In this case, if I wanted to deploy it across 2 different computers, I can go ahead and then partition my data frame across those 2 particular servers. And then when I'm applying transformations on my data, it can be done in parallel. So that's one of the great things about being able to then still use pandas, but then leverage something like Dask for kind of your parallel computing. But now the functionality also extends to be able to leverage Dask to do parallel computing associated with GPUs. So not only can you now use Dask or QDF to use pandas API to just run all your standard functions on a GPU, but now you can leverage Dask to now run it on a series of GPUs. So in this case, if I was just running my standard Dask components and I wanted to go ahead and pull it in to a Dask data frame on a GPU, I'll go ahead and do that. So, or excuse me, if I wanted to go ahead and if I'm still on CPUs and I wanted to bypass the pandas directly and just pull it into a Dask data frame on a CPU, I would just go ahead and specify a Dask data frame, read CSV, and it would immediately be pulled in there, versus if I was using something like a pandas data frame and then going ahead and then distributing it out after I've already imported it into a pandas data frame. Dask QDF essentially does the same thing, except instead of taking a pandas data frame, it's going to be looking for a CUDA data frame, a CUDF. So I'm going to go ahead and import my QDF function into my movies data frame. Now I'm going to turn it into a distributed Dask QDF, where I use my from QDF function, apply it on my data. And in this case, if my server only has 2 GPUs associated with it, I'm going to partition my data into 2 different partitions. And now I'll be able to analyze larger data sets now that I have a series of GPUs to be able to process this data in parallel. The final thing I'll just show is that if I just wanted to go ahead and import my data into a Dask QDF right away and bypass loading it into just a QDF itself, you can go ahead and just do the Dask QDF read CSV function. So the goal of this particular notebook isn't necessarily to show the full suite of transformations that can be applied on a distributed data frame using Dask on a GPU. It's just showing that here's how you get your data in. It's very easy to do. The results return as expected, and now you can go ahead and start getting rolling and start performing kind of the series of actions you do when you're performing your data exploration, your data analysis, your data preparation, and your feature transformation, all along associated with the order of operations of the data science workflow. And that's it. I thank you very much, everybody. I appreciate it.
Thank you, Justin. This is brilliant. I really love, you taking the time to walk us through these great examples, how you can transform from going from pandas to QDF with such such a big ease. That's really, really cool. Thanks for the time. If we have any questions, that will be good time right now to ask them. So I'm going to give the audience a little bit of time. Okay. I don't see any questions right now, but I actually have one short question. So you mentioned some differences between doing things in pandas with pandas on QDF, on DataFrames and QDF. Do you have any other examples or can you talk to any other instances where the API is slightly different?
There's a couple of variations associated with, applying, in pandas you can do user-defined functions. Mm-hmm. And those can typically be applied on strings fairly easily because you have the necessary memory associated to hold the possible variations of a string, and then apply it on a data frame that could be held in memory. Right now they're still being developed, but applying a UDF on top of a string inside a QDF is slightly it depends on the type of UDF you're working to apply it on, but essentially it's a little bit challenging to apply that now.
Gotcha.
Mostly that's associated with the amount of memory available to be able to hold kind of the variation of what you wanted to apply. Essentially, if regex equals this, then if else, call it this, otherwise call it this.
Gotcha. So the conditionals.
Exactly. And so that's kind of being evaluated and something that's still being kind of worked on. But that's just kind of another example of just the slight distinction that you would get. But in some cases, you could identify a solution to around that instead of the straightforward UDF solution, just based on using kind of the built-in QDF functions, similar as you would do in pandas.
Gotcha. Awesome. That's great. That's great. So I'm going to start sharing my screen because I want to, Justin, I think you need to move back to me so I can share my screen. But while you do that, I'm going to start talking about a little bit on Dask. So Dask, thanks for the introduction. This is really great. So Dask allows you to take a workload that would not fit on a single GPU, as Justin mentioned, and distribute it, run it all across multiple GPUs, whether within the same machine, doesn't really matter, or spread across the cluster, and do so with ease. The API changes a little bit, and that actually brings me to the next, point of order for this webinar. If you go to our docs.blazingSQL.com and navigate to use cases and GPU accelerated data science, this is pretty much where you're going to find all the webinars that we have planned for this year or half a year. And also you can find all the recordings that we've already so far delivered of all the webinars that we've so far delivered. So if you didn't get a chance to join us on 16th of February, 2 weeks ago, on accelerated introduction to GPU accelerated data frames in Python, that Justin's colleague Nick Becker delivered for us, then you can go there and then watch it on demand on our YouTube channel. Now, why I mentioned Dask? Because on 30th of March, we're going to have another person from NVIDIA, Jacob Tomlinson, that will walk us through how to do distributed computing with GPUs in Python. And it's going to be also delivered on, as a hands-on session. So if this is something that is of interest, we're going to have one announcement coming out shortly on our Twitter channel and across all the other social media channels with registration links. But if you circle back here by the end of this week, so by I believe that's going to be around 6th of March. I'm making the math in my head, so don't hold me against that. Don't hold that against me. You will be able to just click link to register for that webinar. This is going to be a brilliant webinar. We also deliver webinars in Spanish. So if you are in a Spanish-speaking country, you can subscribe to the next webinar, which is going to be the introduction to QDF for pandas users held in Spanish. Is going to be delivered next week on Thursday. Lou is going to be the host for that one. And then as you can see, we hold these webinars every other week, English versus and Spanish. So there's plenty of content coming up. The next one after this in English is going to be on Introduction to Blazing SQL. So we're going to dive in a little bit deeper into what Blazing SQL does and how you do things with SQL on GPUs using Blazing SQL, and how does it fit into the whole Rapids ecosystem. So that brings me to the end of this webinar. I wanted to thank, again, Justin for taking the time to prepare the content for us and for delivering this really, really great tutorial on how do you switch from pandas to QDF. And I wanted to invite you for the next one. Thanks very much. Thanks, Justin, again.
Thanks, Sam.